Hello and welcome back. Today we're going to talk about encased or composite column. These columns are really great. They have a large amount of load carrying capacity compared to regular column. And normally it's used in tall buildings. So let's take a look at this problem we have here. This column and consists of it's encased. It starts out with the W10 by 45 in the center. And then we have about 8 longitudinal number 8 rebar. And of course, we have the strapping around them and filled in with concrete. And we'd like to know what is the capacity of this column is. Normally, a designer, when they do a big, tall building design, they probably have a bunch of sets of standard details. Something like this could be round column or square column, and they go ahead and use these, and then you can analyze the capacity of it. And what we're going to do here, first we're going to go ahead and find out if they used enough rebar, and check out the spec, make sure this is meet the specification. So the first thing we do is here, let's find out all the problem says is a W10 by 45, and it says, let me look at it, ASTM 8992. So if we go to table 2-4, we know that means basically our FY is equal 50 KSI and FU is equal 65 KSI. Then I'm going to go into table ASC, table 1-1 for a W shape 10 by 45. Get all the information out from the table 1, which my area is going to be area of the steel. 10W is at 13.3, and so on and so forth. Find the D is equal 10.1, and find the moment inertia in X and Y direction. This is the cross-sectional of the area of the column. Because this is the cross-sectional area of the column, and we're going to get all the property for this cross-sectional. We already have the cross-sectional property for the W shape, which we write down. So let's get everything for the rest of the stuff. Get the concrete, the area of the concrete, AG is equal, we said this is a 24 inch by 24 inch. H1 is 24 and H2 is 24. And so we got 24 times 24. And that is equal 576 inch square. The next thing we want to find out the area of the longitudinal rebar, which are these blue dot I have here is 8 of them. So area of steel rebar is equal, and if we look at it, guys, this is a number 8. And if we look at the chart, I have number 8 being as 0.79 inch squared that per each rebar. And we said we had 1, 2, 3, 4, 5, 6, 7, 8 of them. So the area of steel rebar, this will be the area of steel rebar of one of them. For all of them will be 8 times 0.79, which is equal 632 inch square. So now we know that. So the next thing we want to find out what is the area of the concrete. So the area of a concrete is basically the entire area, gross cross-sectional area, minus the area of the steel, which is the W shape, and minus the area of the rebar. And the area, so AC comes out to, just continue it here, it became 576, minus AS came out to 13.3, and minus the rebar came out to 632, and that is equal 556 inch square. Find out the moment inertia of this composite shape. We had IX and IY was given for that, and let's find the moment inertia of the individual rebar and then the whole thing. Moment inertia is ISR, individual steel rebar. Individual is the bar divided by 64. So that becomes our pi, and the diameter of the number 8 rebar is 1 inch. So 1 divided by 4 divided by 64, and that comes out to 0.049 inch by power 4. Now, if you remember when you took Mechanic Material 2 in your second year in civil engineering, you found out the moment inertia was I equal Ix plus AD squared. So this shape is the same way, and we have 8 of these, and we want to find out what is the moment inertia of all this rebar respect to x and y axis. Because it's symmetric, so I and x and Iy probably is equal. So let's go ahead and say Ix is equal I of SR is equal summation I SR individual plus summation of I is equal 1, and this should be I is equal 1, and this also n of area of SR times E squared, or we used to say D squared, because it's a circle here, so it's different. So let's find out what that comes out to, and we have 8 of these bars, so it's going to be 8 times 0.049 plus now we have 6 of these. If this is my x and y, these two right on a y line, so we're not going to worry about that. So if we're doing the x one, let's find out 1, 2, 3, 4, 5, 6 of these has a distance from here to the y, and that's what we're going to have 6 times a is a 0.79, and our E or D, it basically comes out from here to there is about 9.5 inch, so times 9.5, and that is squared. Then plus we have 2 more remaining, 1 here and 1 there, so it's going to be 2, but the distance before these two are 0, so it's going to be 2 times 0.79 times 0 squared equal 428 inch by power 4. One thing we didn't mention here is the modulus of elasticity of the concrete is 3,900 KSI. Go ahead, calculate the concrete moment inertia, and ICX is equal I of the total section GX minus I of SX, the steel, and minus I of rebar, which is equal the because that's a square shape, so it's going to be 112 BH cubed, which is basically 24 times 24 by power 3, and minus SX came out to be 248, and the other one came out minus 428. So that comes out to 27,000 inch by power 4. And let's calculate the ICY also, which is the same formula basically. And IGY, it's the same number, minus I of SOY, which was different, 53, and minus ISR, which is the same thing because it's symmetric. Now that comes out to same thing, 112 times 24 times 24 by power 3 minus 53.2, 53.4, and minus 428. So that comes out to 27,200 inch by power 4. So this is all the information pertaining to this cross section. And now we have that. This is our column. This is the way our column is loaded. It has a dead load of 260 kip, life load of 780 kips, and it's 14 feet long. And now we have found all the information. We're going to continue to the next stage. We're going to do our structural analysis on it. So I'm going to go ahead and erase this board. Like a regular column, we're going to check out everything. So first we're going to check the local buckling. And you can tell this section is compact, so you don't have to worry about local buckling. So there's no worry there. And the next thing we're going to check the material limit. And that's going to be per basically C specification. First, we're going to look at the concrete strength, and the strength has to be between 0.3 KSI and 10 KSI. So we're going to say our F prime C is equal 5,000 PSI concrete. That's what is given. So that's kind of checks out because it meets that specification, and it's between 3 KSI and it's more than 3 KSI, and it's less than 10 KSI. We're going to check out the strength of the steel, and per spec, the steel is supposed to be less than 75 KSI. So our Fy is equal 50 KSI, and that is less than 75. We check out there. And the next thing, we're going to check out the strength of the rebar. So we have 3 different types of material in this composite column. We got the steel, we got the concrete, we got the rebar. And we're going to check all 3 of them out to make sure they meet the specification. The first 2 so far did. And the rebar is, the spec says has to be less than 75 KSI. Rebar, Fy, rebar is 60 KSI. And that's less than 75, we good. So our material specification checked, no problem. So next thing we're going to look at is the transverse rebar. So these are the transverse rebar right here. And these are number 3 at 12-inch spacing. So we got one going around the inner rebar, and the other one going out, tying the outside rebar. And let's look at the spec, what the spec says about that. And we see on the board, the spec says transverse reinforcement limitation provided in AAC specification section I1.C and I2.1B, which I have down, and also ACI 318, is basically saying they require that the lateral ties or spiral be used for transverse reinforcement. When lateral ties are used, a minimum of either number 3 rebar and spaced at 12-inch. So we are using minimum number 3 rebar, so we good in that spec, and that checks out. Minimum number 3 at 12-inch spacing. Checks out per the spec. Another requirement per spec down here, it says per section I1.1 as A, maximum tie spacing should not exceed 0.5 times the least column diameter. So SMX basically has to be half of either H1 or H2. This is a square, so it's going to be 0.5 times 24, which is equal 12-inch. And ours is a 12-inch, which is less than or equal 12-inch. Okay, so we check out there too. So now the next spec we're going to check out is the concrete cover. And ACI section 318, section 20.6.13 contain concrete cover requirement, which it says basically it has to be minimum of 1.5 inches. And our cover in here came out, as you can see, our cover came out to be 2.5 inch minus diameter of the bar, which was 1 divided by 2, and then minus the diameter of the, which itself it was 3/8. diameter of the transverse, the number 3, and that comes out to 163, which is more than 1.5. We check there too. Another requirement of the specification says ACI specification section I2 and A3 and also ACI 318 for additional transverse tie requires basically says that ties are required to support longitudinal bar located further than 6 inch clear on each side from a laterally supported bar. So we do have provided that anyway. So that checks out because we have 2 lateral support on outside and then on the inside at 12-inch spacing. So we're going to move on to the next specification. It says the steel limit. Longitudinal and structural steel reinforcement limit are provided in AICS specification section I1, 1 and I2, 1. It's basically saying the area of the steel compared to the total area of the column should be bigger than or equal than 0.01. And in our case, it's going to be 13.32. Divide that by which we erased the total. I erased it. It was on the board. The total area came out to 576, and that is equal 0.0231, which is bigger than 0.01. We check out. Then the same spec says also the total area of the rebar divided by the total area of the cross-sectional area of your column should be bigger than 0.004. So we're going to have basically AS of rebar divided by AG, which is equal to the total area came out for the rebar, if you remember, which I erased, was 632. 6.32 divided by 576, and we have 0.0110, which is bigger than equal than 0.004, and we check out there. We go back to the same spec, same section, I2.1. It says the total area of the rebar divided by the total area of the gross cross-sectional area for maximum longitudinal reinforcement ratio has to be less than 0.08. So this number, also 0.004, is less than 0.008. We check out there also. And here's another interesting section of the thing. The bar says the required minimum of 4 longitudinal bar within a rectangular or circular member with ties, and 6 bar for column utilizing spiral ties. The intent for rectangular section is to provide a minimum 1 bar in each corner. So we already met this requirement. We exceeded it, so that's good. We have 8 bar, more than 4 and 6. That's not a problem there. Continue with this spec and also ask for a required clear distance between the bar should be less than 1.5 times diameter of the bar. So that's basically saying that our S minimum is supposed to be 1.5 times maximum of 1.5 times dB divided or inch and a half period. So both comes out to 1.5 anyway, because since the diameter of the bar is 1 inch, so that's equal 1.5 inch, and our maximum is, so our S is equal, we have right here 9.5 inch, so 9.5 minus the 1 inch diameter for the bar itself, and that comes out to 8.5, which is bigger than 1.5. We check out. Another spec, it says the closest rebar to each other, clear spacing between longitudinal bar and the steel core. So really the closest one will be this one right here to that, unless we figure out what it is. And that was the formula says that S minimum should be same thing, 1.5 inches. And therefore our S is going to come out to for the closest one, it's going to be, if you go from here to here, that's a 12 divided by, that's 24 divided by 2, which is 12. So that's going to be basically h2 divided by 2, and then minus diameter d divided by 2, diameter of the bar. And then we have the cover right there itself. You got that cover, which is 2.5 inches. So minus 2.5 inch cover. And then minus the diameter of the bar divided by 2. So our D, this D is divided by 2 is, this is the D. And D came out to be, for the steel, 10.1 inches. So let's plug all this in right here. That became H2 24 divided by 2 minus 10.1 divided by 2. 10.1 divided by 2 minus 2.5 and minus 1 divided by 2. That comes out to 3.95 inches, which is bigger than 1.5. We check out. The spec is calling for, it says, what is the longitudinal cover for the concrete cover for the longitudinal reinforcement? And that's basically ACI 318. The required is supposed to be same as the tie cover, and which we already talked about it. So that's the 2.5 inches. So we good, which is more than we already covered that. So this was basically the specification. We made sure so far this cross-sectional of this column meet both AICS specification and ACI specification. Now we can go ahead and analyze the strength of this column. Let me erase this. So now we're going to go ahead and calculate the capacity of this column, which so far it meets the specification. So we're going to use both systems here, load resistant factor design and allowable stress design. In load resistant factor design, the load combination comes out to 1.2 times dead load, which is 260, plus 1.6 times life load, which is 780, and that comes out to 1,560 kip. That's quite a bit. And in allowable stress design, our load combination is basically add both load. So this will be basically PU equal, and this one is a PA is equal 260 plus 780, and that is equal 1,040 kip. So the next thing we're going to calculate is the nominal actual compressive strength without the consideration of the length effect, P&O. And P&O basically is given basically Fy of this steel times area of the steel, yield strength of the rebar times the area rebar, and the concrete, which would be 0.85 F prime times AC. Let's go ahead and do this. So that comes out to 50 KSI times the area came out to be 13.3, plus this was 60, and the area was 632, 6.32, plus 0.85, 5,000 PSI. So that's a 5 KSI, and multiplied by the area of a concrete came out to be 556. And that is equal 3,410 kips. The next thing we want to do is to calculate the PE. If you look at the spec right there in section 1B, it says we need to calculate PE because we want to know the ratio P and O divided by the ratio of PE, whether it's going to be less than 225 or more than 225. But in order for us to calculate PE, we have to calculate PE is basically equal from equation I2-5 is pi squared times EI effective divided by effective length. And if we go to the next page of that spec, it says EI effective, the effective stiffness of the composite strength is based on basically you have to know what is the coefficient for calculating the effective rigidity. So now we're going to move into equation I2.7, and that basically says equal, give us C1 equal 0.25 plus 3 times area of the steel plus area of the rebar, and divided by the total cross-sectional area, and that should be less than or equal 0.7. And therefore our C1 comes out to 0.25 plus 3 times the area of steel came out to 13.3 plus the area of the rebar came out to 632, and divided by the total area came out to 576, and this comes out to 0.352, which is less than or equal 0.7. Therefore C1 is equal 0.352. Now we're going to go back and use equation I2 .-6. And from there we're going to calculate the effective EI effective, and that is the effective stiffness of the composite section, which comes out to ES times IS, the lesser of the two, which is ISY, and plus ES times moment inertia of the rebar, and plus the factor C1 time for the concrete is used, EC times I of concrete in Y. And therefore this number is going to come out to 29,000 KSI, we know that, multiplied by ISOY came out to be 53.4 plus rebar still the 29,000 KSI time 428, which is the moment inertia for the rebar, and plus C1.352 time 3,000. Come back in here time. Just do this here. Plus 0.352 time the EC comes out to 3,900, and the ICY came out to 27,200, and that comes out to 51,300,000. That the unit for that is kip inch square, not per inch square, kip inch square. Going back to the equation, let me do this different color here. Okay, going back to equation I2-5, and we're going to calculate PE, which is equal pi square time EI effective divided by LC square. Okay. So we're going to go ahead and calculate the elastic critical buckling load from this equation, which is P is equal pi square EI effective by LC square. And our LC basically is a KL, and our K comes out to 1 because this is pin on both ends. So K is equal 1. So the effective length comes out to 14. And therefore we continue with that. That becomes pi square. And this number was 51,300,000. And divided by 14 times 12 inch to make that an inch by power 2. And that comes out to 17,900 kips. Well, now let me erase this. We're going to continue. So now we want to find out what's the ratio P and O divided by PE per spec in section I-2, whether it's going to be less than 2.25 or it's going to be more than 2.25. So that came out to 3,410 divided by 17,900. So that comes out to 0.91, which is less than 2.25. And per spec, that means we can use equation I2-2. So now, because of this, we can use this equation. And therefore, this comes out to Pn, comes out to Pno, which came out to be 3,410 times 0.658 by power of 0.191. And that gave us basically 3,150 kip. So now we have that. And I need my LFRD again. So if I come back in here and divide this by 2, we say this is ASD and this is load resistant factor design. And the phi for this one is per spec is 0.75, and omega for this one is equal to. So now we have our number here. So we're going to say phi times Pn is equal 0.75 times 3,150, which is equal 2,360 kip. And remember, our load came out to 1,560 kip. So 2,360 is bigger than 1,560. We check out there. And in here, we're going to have P and an allowable stress design divided by omega. And that comes out to 3,150 divided by 2, which came out to 1,580. And that is more than 1040. And that checks out. Now remember, the capacity of this composite column came out in load resistant factor design, came out to be 2,360 kip. And our applied load was 1,560 kip, so we're good. So if you look at allowable stress design, our capacity per allowable stress design is 1,580 kips, which is more than applied load of 1,040 kip. So we're good. But the spec also says, wait a minute. I want you to know what is the capacity of the column, steel column is. Calculate that to make sure this is not more than that, which is not going to be it anyway. So we're going to go ahead and calculate the capacity of that. Because we know that's a W10 by 45, all we have to do is basically go to table 41A and find out where W10 by 45 is. And let me do that in different color, go green. W10 by 45, we look at that from the table. This was for the composite column. And this one is going to be W shape. So for the composite column came out this. For W shape, it's going to be basically from the chart, we have a phi times Pn comes out to 359, which is way less than a capacity of that. We don't care about that. And Pn divided by omega is 239, which is way less than 1040. So just to make it a comparison, the column capacity by itself is 359. But when we put composite, we put all the rebar there and put a concrete there, it brings it up to 2,360. That is the difference. I hope this was useful. If you like it, please give me a thumbs up. Have a good day.